Okay, so let me introduce the speaker. Although he does not need any introduction, but still, let me introduce Yoshua. Okay. So Yoshua, as you know, is the world recognized leader in the field of artificial intelligence. He is known for his work in pioneering work in deep learning, for which he earned the Turing Award in 2018, along with Jeffrey Hinton and Ian LeCun, which we know is the Nobel Prize of Computing. Okay, so we are very lucky to have him with us today. He's a full professor at University of Montreal, and he's founder and scientific director of MILA at KBCG Institute. He co-directed the CFAR Learning in Machines and Brain program as senior fellow and acts as scientific director of IVADO. In 2018, he collected largest number of citations. I was looking at his citations on Google Scholar. Please do it. it's amazing. Okay, and he's concerned about the social impact of AI and objective that AI benefits all. And he actively contributed to the Montreal Declaration for Responsible Development of Artificial Intelligence. Without wasting any further time, so I'll hand over to you, Yoshua.
Thank you, Yasin. Let me share my screen. For your information, when you're speaking in front of the camera, it works well that we hear you, but otherwise it's hard to follow. All right. So yeah, I'm going to tell you about model-based machine learning, its relationship to reasoning, especially causal reasoning, and how this may be building blocks towards designing AI systems that can behave like scientists, which I call an AI scientist. In other words, trying to understand how the world works. So maybe a good starting point motivating a lot of this is what's missing from the current state of the art, like ChatGPT. And I think many people will agree with a lot of that list. Reasoning, especially the way I think about reasoning, the way humans reason, and being able to generate statements based on an estimate of their truth rather than how likely that they are to appear in human text, which are really two different things, including reasoning about cause and effect and discovering the cause and effect relationships, being able to provide high-level consistent explanations for what the system produces, being able to generalize better out of distribution. I mean, it's interesting that these systems need a lot more data, at least in terms of text, than humans need. A lot more, meaning like tens of thousands of times or hundreds of thousands of times more data than the human needs. So there's a problem of sample complexity. The question of reasoning is connected to the notion of system 2 versus system 1 that I've been talking a lot in my talks for the last 6 years now. So I think current deep learning does a pretty good job at system 1, in other words, intuitive capabilities that are mostly unconscious. And we see some progress with the state-of-the-art language models, but still not very satisfying in terms of reasoning abilities, sequential, logical, algorithmic planning, and so on. So also, even the very way that we're training these systems probably doesn't correspond to what we want if we want systems that reason. So as I said, they mostly focus on you know, how often, if you want a sequence of words could happen. Whereas if you want to reason, if you want to produce things that are true or estimate their probability, then you want to reason about statements like, you know, the newborn is a female, maybe a statement. And yeah, it should be about 50% true in general. Whereas the sequence of words, the newborn is a female, is should have a probability that is much smaller, because that's out of all the possible sentences, this is going to be a tiny probability, right? So we're really not even talking about the right probabilistic objects in large language models. Also, I think it's important to consider specifically the way humans reason, because of course in AI there's been decades of work in reasoning and symbolic AI. So what's special about the way humans reason? A good starting place to get a good handle on this is the global workspace theory, which dates from the 90s, but on which there's been a lot of work in neuroscience, for example, by the group of Stan Dan and many others, and is currently a dominant theory of how conscious processing works. So for this, you can think of a thought as being well captured by a short sentence involving very few concepts. And these thoughts emerging stochastically as inference over just a few latent elements like the words in a sentence. And finally, of course, these thoughts come sequentially one after the other in a train of thoughts. And these train of thoughts, they don't contain full descriptive information about a plan, about an explanation or something. Only partial information, but very informative information. So I've tried to come up with a set of desiderata derived from everything I know about human reasoning regarding the sort of inductive biases we may want to consider for machine learning, especially deep learning systems that reason. So one of them I'll talk a lot about today is the separation between understanding how the world works, the world model, and the machinery that allows to answer questions, or the inference machinery. Second one, of course, is that the world model should be probabilistic in the sense that statements about entities in the world are usually uncertain. We need to deal with the fact that the number of possible statements is exponentially large. So think about the number of possible thoughts. But only a few can be considered at a time. That's the bottleneck of the global workspace. And because each statement involves very few variables, if you think about the statistical dependencies that they can express, they must be part of, it must be consistent with a very sparse dependency graph that where each factor in the factor graph connects with very few random variables. Also, the world model itself is unknown. Like the brain is able to deal with uncertainty not just about latent variables, but about knowledge more broadly. So Bayesian uncertainty, and this is a big challenge. I'll say a few words about that. Let me see. Something that's people in this crowd probably have been thinking more about is that knowledge in this world model is broken down into pieces that are reusable. Most of the statements that are being manipulated are latent, so you can only make inferences about them. These inferences can be revised as we observe more data. The set of symbolic entities that these statements are about isn't a fixed set. It's growing as we kind of make up new concepts, as we discover new words and so on. And furthermore, and this is something coming from neuroscience, but of course that's anchored in deep learning as well, these symbols are associated with high dimensional, probably continuous representations that help in terms of generalizing across all these possible statements. And finally, a thing I'll talk a lot about today is that a lot of these statements are about causal variables. In other words, variables that can be changed, that can be intervened by agents, thus changing the distribution of the data. Okay, so let's talk about the model-based aspects of things. Current deep learning mostly is not model-based. Current deep learning is trained end-to-end. So if you look at LLMs, we directly go from questions to answers. But there's a lot of evidence that the brain is able to manipulate information as if it had a model of how things work. We can do counterfactuals. We can plan in a kind of explicit way. And we also have the ability to make up new abstract concepts to help us capture how things work. So why would be interesting to decompose the task of making predictions into first learning how the world work, and second answering questions about it, which is inference. The main reason is that the question answering or the inference machinery, if you do that separation, the inference machinery can be trained in a way that is not limited by the amount of data, but only limited by the compute. So think about AlphaGo. In this case, the world model is handcrafted. This is a set of rules of the game of Go. And the way that the inference machine, which is just the playing policy, is trained, doesn't require to, for example, imitate how humans play. It only needs to refer to the world model, which are the rules. So in the case of AlphaGo, you get self-play. The world model itself, of course, depends on what we observe in the real world. It needs to be trained, and the complexity of the world model should grow with the amount of data that is actually available. If you have a single neural net that both has an implicit world model and answers questions as doing inference, then what you end up is that as far as modeling how the world works, the world model part is going to be overfitted, because the optimal capacity for representing how things work is usually much smaller than the optimal capacity for answering questions. So again, if you go back to the game of Go, the rules is one page of the world model is one page of code or text, whereas the optimal inference machine is huge. It's actually exponentially large, and we approximate it with a very large neural net. And that's true in many, many settings, that inference, the computations needed for inference are much more complicated than the set of rules that explain how things work. So again, think about, say, physics. Usually we can write the equations that explain how things work with just a few lines, but actually then running simulations or running computations that allow us to answer questions, let's say in chemistry, require huge amounts of computation. And these huge amount of computations are complex. They will, if going to be approximated by a neural net, that neural net is going to be big. But if the same neural net is both doing question answering and capturing how things work, then the part about capturing the world is going to have access to too many degrees of freedom, so it's going to overfit. And because you don't want to overfit too much, you're going to tend to make it not too large either, or stop early, and then you're going to underfit on the inference. If you separate these two jobs, then you don't have that problem. Another thing, of course, that people like Bernard Shopkoff and others have been talking about is that we would like our world model to break down knowledge into pieces that are independent, as in changing one piece doesn't mean you need to change the others, right? So when you write code, you would like to have that property as well. And causal modeling has been kind of made with this in mind, where each causal conditional distribution is parameterized separately. So let's talk about causality. So what's different between a causal model and a regular distribution? Well, we we have something different in the causal model. In addition to the regular random variables that I called V here, we have other special variables, the interventions that I call I. And what a causal model specifies is not one distribution, but it's a family of distributions over these random variables V, where each element of the family is corresponding to one intervention, one value of the intervention variables. So if we decide to set some variables, specific variables to some value and let the others untouched, then we get one particular intervention and we get one particular distribution, joint distribution over the V's. So we've got this big family, and you can think of it actually as a mixture if you assume that there is some distribution over interventions. Now, what's interesting about that family of distributions is that they all share the same parameters, which means if you're able to learn that the causal model, in other words, this joint with the notion that you can intervene on the variables, then you can generalize out of distribution to other members of the same family corresponding to interventions you've never seen. Now, I'm going to argue something that is maybe not the way you hear about causality typically, which is that you can think of causal reasoning as probabilistic inference when you include the intervention variables in your graphical model. So the way that they should be included is corresponding to what people call intervention surgery. So for example, a typical intervention like the do intervention from Perl, what it does is that it sets one variable to a particular value, and this way it ignores the parents of that variable. And what you do when you do that is just change the mechanism by which this variable is set. Now, once you do that, you can apply regular rules of probabilistic inference to perform reasoning in causal models, including for cases where maybe some of the variables are observed, some are not, or some of the interventions are observed and some are not. So the rest of my talk is going to be focusing on how we can do the kind of probabilistic inference we would like. Oh, the other thing I want to say about causality is, if trying to put it in the framework of machine learning using maybe words that people will agree on, so how is that different from other things we do in machine learning? Well, this kind of structure I just briefly described is a kind of inductive bias. It says that the way that the variables we are modeling or we are observing are related to each other satisfy this very special property that I outlined with the notion of intervention and the family of distributions that are associated with the interventions. And there are also other constraints like temporality and marginal independence of causes that come with the relationships between those variables. So really, causality is about putting a constraint on the kind of distributions that we would like to learn. But there could be other inductive biases from the system to abilities of humans that we may want to throw in, of course. So another one I mentioned, the ability to do Bayesian inference. In other words, take into effect that we have finite data sets and that there could be multiple models, including multiple causal graphs that could explain the data. In particular, researchers in causality talk about the Markov equivalence class of causal graphs, that all the graphical model structures that are compatible with data, even an infinite data set, would still leave ambiguity about what the right graph should be. So you can't just pick one of those graphs because it could be wrong. Really, the only rational way of dealing with that ambiguity is to somehow perform inference, answer questions, taking into account the fact that there will be multiple possible models and multiple possible graphs. Now, that's even with infinite data, but if you have finite data, you have another source of ambiguity, right? Just due to the finiteness of the data set. And so one natural way to think about all of these sources of ambiguity due to the finite data and due to the kind of notion, the structure of causality, is to estimate a Bayesian posterior over the causal model. So this is what my group has started to work on. So you'd like to represent implicitly, because it's too rich to be enumerated, a distribution over all the possible causal graphs, including latent variables that maybe you don't even know how many there are, including, of course, the parameters that specify the relationships between those variables, given the data, which may be a bunch of observations. So, so this looks like a formidable object, but actually that distribution is proportional to a quantity that we can compute, which is the prior times the likelihood. And likelihood is something that's as big as the data set, and takes linear time to compute in the data set, but we can approximate it stochastically by taking a mini batch. So actually we get the posterior, but only up to a constant, and it doesn't tell us how to sample from it. But I'll talk about GFlowNets, which are a way to convert such an unnormalized function, density function, probability function, into a sampler and also amortization machinery. Okay, so in order to do the kind of probabilistic inference that I think we need for reasoning, you could use MCMC methods, and you could also use variational methods. These are two main approaches. The MCMC methods, well, they are very computationally expensive, and the main reason is that if the distribution you're looking to sample from has many modes, many places where it's high, and these modes are well separated from each other, then it can get very, very difficult to visit all those modes. Even jump from one to another becomes exponentially difficult in the distance between those modes, because the MCMC is making one small stochastic move at a time, and it wants to stay close to where probability is high, and the chance that it makes a lot of small probability moves becomes exponentially small. So we'll talk about GFlowNets to try to do that, but they're maybe part of a bigger set of methods, including variational methods, where we are going to do amortized inference. So in other words, instead of trying to answer a question by doing a lot of computation like MCMC at runtime, we're gonna pre-train, if you want, a neural net that's going to be fast. It's going to give us answers quickly. So that's what amortized inference is about. We pay a lot of price to pre-train a neural net, but then at runtime we can get answers quickly. So that will replace MCMC, so that at runtime we can get answers quickly. But there's another advantage, which is that it can sort of give answers about modes of the distribution that it may have never seen during training. And this is just a side effect of the power of generalization, which is what we get in machine learning. So one way to think about these amortized inference methods, so if you think about like the figure on the right here, let's say you've seen these three modes, the red bumps, during training of the model. Machine learning methods should be able to figure out, hey, I've seen these three and they kind of fall on the grid. Maybe there's another one at this other grid point. Right? So generative models can do that kind of generalization. And indeed, they do. And you can train amortized inference machinery with exactly the same sort of properties. And they can be used both for sampling actually and summing or amortization without having to explicitly visit an exponential number of modes, for example. So now going back to our task of probabilistic inference for reasoning, the kinds of objects we want to be able to reason over are compositional. And a natural way to deal with compositional objects is sequentially, which is also something that you get in your brain, of course, when you think through a sequence of steps. So the GFlowNet learns a stochastic policy that decomposes the generation of a compositional object, like a data structure, like a graph, into a sequence of steps. So think about generating each edge of the graph at a time. So we wrote a lot of papers on GFlowNets. The first paper came out at Europe's 21, almost 2 years ago. And it shows a lot of the important basic idea, but in simple terms, I mean, the original view of GFlowNets was as a reinforcement learning method, where instead of generating a sequence of actions that get to maximize a reward, which is what we usually take as the objective in reinforcement learning, we're trying to use that sequence of action to construct an object x with probability proportional to the reward r of x. So we're given a reward function rather than being given a data set like in normal generative models. This is more like RL, where you're given a reward function. And instead of maximizing the reward like in RL, we're trying to sample proportionally to it. So you can think of a neural net that takes for example, a partially constructed graph and outputs samples a decision about which piece to add to the graph to get the next stage in the construction of the graph. And there may be a special action that says, stop, we're done with this compositional object we'd like to build. So it essentially learns a policy. So we wrote many more papers, but another connection I wanted to make is between GFlowNets and variational inference, because as I said, variational inference is the other broad set of methods for probabilistic inference. And yeah, the GFlowNets can be cast as variational inference with a special objective function that a special loss function, if you want, that has the property that they can be trained off policy or offline, which is different from the elbow objective that is typically associated with variational inference. And as a consequence, you can avoid some of the big problems that exist with current variational inference, which tend to get stuck around one of the modes of the distribution you're trying to sample with. And so with GFlowNets, you can sample highly multimodal distributions, which are tricky with variational inference. The GFlowNets, as I said earlier, they also allow you to perform amortization. So what is amortization? Well, it's summing an intractable number of terms. So let's say I would like to compute that sum S of x equals sum over y of r of xy in the first line. And the number of terms is really large, so I can't actually run that sum. So we're going to do two things, actually. We're going to estimate that sum, S, with a neural net, S hat. And we're also going to train a sampler, pi of y given x. And that sampler is going to be estimated with, we wanted to sample proportionally to r. So since S is the sum over y of r of xy, then what we want is pi of y given x be the ratio of r of xy over S of x. Now you can turn the second equation into the third one as a constraint. In other words, there's a relationship between the sampler and the amortizer that their product should be equal to the reward function r of xy. And we can turn that constraint, which should be true for every xy, into a loss function. And that's the fourth line. And that's the general form of the objective functions we use in GFlowNets. So they train two neural nets, if you want. One that computes intractable sums, and implicitly, of course, it doesn't actually do it. And so it estimates those sums. And the other that learns to sample some random variable given some other random variable. Again, something that we would otherwise not be able to do, and we're going to approximate using machine learning. You can generalize that to sample sequences, as I mentioned, but I won't have time to go into those details. But basically, instead of sampling in one step, like the sampler here, you sample through a sequence of steps. And now pi is a policy. It's not just a distribution that you get in one step. But otherwise, it's going to look very similar to this. So one of the lines of work we've investigated that connects very much with the subject of my presentation is the use of these GFlowNets to sample from the Bayesian posterior over causal graphs. So if you want to do causal modeling, one of the most difficult parts of it is to come up with what's the causal graph, as I mentioned before, that fits the data. But you want to be Bayesian, as I try to motivate. So really what you want is a sampler for all the possible graphs, but sample according to their posterior. So the GFlowNet will sequentially construct a graph. And so it starts with like the empty graph, and then it may add an edge, then another edge, and then at some point it may decide to stop. And then you can continue and do things like sample the values of latent variables or parameters. So the first paper on that line of work was published at UAI last year, and last summer, but now I have several other papers following up on this. Okay, my last slide. So in the title, I talk about an AI scientist. So an AI scientist, the way I think about it is an AI system that tries to come up with theories that explain the data. And the reason I'm saying this would be like a safe AI system is that it doesn't need to be an agent. It's just trying to figure out how the world works. And that's the world model part, of course. But if we also train the inference machine that allows to answer questions, which I outlined of how it may be done using, for example, things like GFlowNets, then we can get something like an oracle that humans would be acting in the world using those answers, and you wouldn't need reinforcement learning, fine-tuning as we're doing right now, and you wouldn't want to put it acting in the world directly. It wouldn't have any strategy, it wouldn't have any goals, and so you couldn't lose control, which is an issue that many people, including myself, are with the path we're taking currently with AI. So thank you. I'm happy to answer questions.
Thank you.
Yeah.
So we have some time for question answers. Anyone who want to ask questions have to come here, please. So there is some motivation. So yeah. Can you come here, please? So Yoshua can hear directly. So we are using the mic of this machine. Yeah. So you can just stop.
Hello.
Yep.
I want to ask though, in my view, those probably.
Can you come closer to the computer?
Yeah. I think those probability inference is more it's more casual version.
Can you speak towards me and not the side? Like I don't hear half of what you're saying. Just face me, not on the side.
Yeah, just face here. Look at the left. So I need the mic. Just where is the mic? Just look to Yoshua. I believe. No, but that is not.
Those probability inference you said before is more.
Hello? Hello?
Sorry. So just keep looking at the screen, and I think it.
Yeah, don't look at the at the big screen. Look at the small screen.
Small screen.
Yeah.
The laptop.
I want to ask how to acquire the causal relationship in the psychology view. That what can we get, or what the things will be if we do the action X.
You're asking how such a system could learn about the effect of an action?
And I want how to acquire the causal relationship in the psychology view. That
No,
by
okay.
doing.
So you're here. I'm not talking about trying to imitate humans, because humans indeed take advantage of actions in the world with something like active learning, if you want, in order to efficiently figure out how things work. But if you look at data that has already been acquired and you want to come up with an intelligent set of theories to explain it, this kind of probabilistic inference is doing it. I mean, it needs to be done at scale, which isn't something we've done yet.
Thank you.
So sorry, Yoshua, so we have a strange setup here for the audio thing. That's why there are some issues. We have time for one more question. Anyone? So Joshua, let me ask about the GFlowNet. Can you hear me clearly?
Yes, yes.
Okay, so for the GFlowNets, how do they scale? How do they scale, especially like at the foundation models or large language models
No,
scale?
we don't know how to scale them at that level at this point. We are able to do things like build a causal model with hundreds of random variables, for example. But if you want to do something on the scale of large language models, you would need something much, much bigger. So I think we need some different algorithms to make that efficient. I have some ideas for that, but this is an open problem.
Okay.
I mean, it's the same problem with reinforcement learning. Like we don't know how to train an RL agent over millions of steps. We can do it over hundreds or thousands of steps, but not millions or billions. But this is what we would need in order to do something like equivalent kind of knowledge of the world as a foundation model.
Thank you. Thank you so much, Yoshua. And
You're
thank you
welcome.
for joining very late at very odd time also for you. So we appreciate that.
Thanks for having me.